Okay, welcome back. We are taking a look at this now. So let's see. Our first step, H naught. You could just put O sub I equals E sub I, that's totally fine. And H1, O sub I is not equal to E sub I. Or you could talk about using in the words that they used, which is more correct, but not necessary for the exam. Necessary for homework, not for the exam. So sports preference is independent of the gender of the person, or it's not independent, it's related to the gender of the person. Okay. Step 2, find the critical value. So the critical value is 5.991 because our degrees of freedom is we have 2 rows and we have 3 columns. So 2 minus 1 times 3 minus 1, 1 times 2 is 2. And then we bust out our little chi-square table. Alpha is 0.05 and degrees of freedom 2, and we get 5.991. Great. And then you draw a little picture. Ideally, a little picture. Sorry, should have done that. Right, up and then out. And then you put in your critical value into here. I can't do that. Anyway, so it's 5.991 goes in here. Let's put CV. I can manage that for right now. And then you have to find your first and last expected value. So that's this guy and this guy. You got to find those two. All right, so he's 1, 1. That's easy. E1, 1, and he is row 2, column 3, E2, 3. So the first one, we found his row total, 32, and his column total, 38, and divide by the grand total, 80. So I got 15.2. This guy, his row total is 48. His column total is 16, so 16 times 48 divided by 80. Doesn't matter which one you put in which order. 16 times 48, 48 times 16, they're the same thing. No big deal. It's totally fine. Divided by 80, and you get 9.6. Just find them. You don't do anything else, just find those two. No other thing. You don't have to find all of them. Just find 2 of them to prove to me you understand how to find the expected value from a matrix. And that's for this matrix entry of data. That's all you have to do. Just those 2. Leave them alone, and then put this into your calculator. So get your calculator out. You did second matrix. You went over to edit. And then you put in, it's a 2 by 3, and then you put them all in, 18, 10, 4, 20, 16, 12, double checking to make sure they're all right. And then you did stat tests up to chi-squared tests, and observed is in A, expected is in B, calculate, boom, there you go. So then you have your chi-squared is 2.8, it should have been 9. That's okay. 2.38, 2.39. And then my p-value is 0.303. That's totally likely, so I'm definitely not going to reject H naught. My degrees of freedom is 2 in case you had trouble with that one. As a side note, if you have an 84, you can use this for your goodness of fit tests. You put your observed into list 1 and your expected into list 2. But you still have to write them all out. But you can use that to calculate that if you want. That's the one time when 84 is more useful than the 83. Okay. So now I have my chi-squared. Should pop it in here. It's way over here. My chi-squared is way over there. So it's totally in the do not reject region. It's in the innocent region, so do not reject H naught. And there is not enough evidence to, you can just say, if you want to say, just not enough evidence to reject the claim that the proportions are as stated, or you could say this, which is a little more specific and more accurate, but I'm not going to insist upon that for you guys. Okay. Good? Making sense, more or less?
Professor Young?
Yes.
For step 3, all you want us to do is literally just find the numbers. We don't have to do anything specific with them after we find them?
exactly. Just prove to me you know how to find them by finding two of them, the first one and the last one. That's it.
Okay, thank you.
Theoretically, you would find all of them, but that's too much work, and it's just not. But prove to me you understand how to find them. And the first and the last means that you know how to find them and not just one of them. You know how to find, like, understand the idea of, like, the second row, the next, the third column, that sort of thing. Yeah.
Got it.
So that's all. It's just a small demonstration of your ability to compute the expected values. All right, so homogeneity of proportions is similar, right? It's when you're comparing proportions to see if the proportions are the same, and we are not going to worry about that today. So the next we're going to do that next class. So the next page, skip the next page. So flip the page. We're going to skip the next page, and we're going to go straight on to Notes Chapter 1.3. Or you might have it separately, but Notes Chapter, 11.3. I can't read. Notes Chapter 11.3, One-Way ANOVA. That's what we're doing now. All right, 11.3, One-Way ANOVA. So you guys know when we have, I'll let somebody read. Vanessa, go ahead and read.
When comparing more than two means, the t-test should not be used. This section introduces the method of one-way analysis of variance, which is used for tests of hypotheses that three or more population means are all equal. Because the calculations are very complicated, we emphasize the interpretation of results obtained by using technology. The hardest part of ANOVA will be identifying a problem as ANOVA.
Right. This is going to be super straightforward, really easy. The hardest part, like Vanessa just said, is going to be identifying it as ANOVA. That's not getting it mixed up with the other ones. So again, if we're comparing two means, we just use our regular t-test from Chapter 11. But if we have more than two means, we have to have something else. So that's where ANOVA comes in. So some basic things. The samples must be from an approximately normally distributed population. They should be independent of one another, and their variances should be roughly equal. You don't have to worry about that. I'll take care of that part. But here's our first step. Step 1. H0 is that all the means are equal. Right? Remember, H0 is always equal. In this case, mu1 equals mu2 equals mu3 equals mu4. However many mu's you have, however many lists you have, they're all equal. So if you had 3 lists, you'd say mu1 equals mu2 equals mu3. If you had 4, you'd add in the equals mu4. H1 is at least one differs. That's all you need to write there. At least one differs. Right, just at least one differs. That's all you need. Keeping it simple. All right. If there's no difference between the means, then the between group will be about the same as the within group, and we do not reject the null hypothesis. It'll be close to 1. However, when the means differ a lot, then the between group will be a lot larger than the within group, and we reject the null hypothesis. Since we're comparing variances, this is called an analysis of variance, ANOVA. Okay, here's our test stat for this, which you do not need to know how to calculate in a sense because it's really complicated. However, you should realize it's the variance between the groups over the variance within the groups. So on the exam, I will give you the between group variance and the within group variance and some other confusing stuff like alpha, n, or n1, n2, n3, or whatever, I don't know. And I will say compute the F statistic for this. And this is, all you got to do is take the between group variance and divide by the within group variance, and then you're done. That's it. Nothing complicated. So make sure you know that's written down on your notes about most of the way down towards the bottom. It's in big, big, big letters because I do expect you to at least realize that that's the idea. It's the variance between the groups compared to the variance within the group. It's that ratio. And I will go over that more next class again with the visual, but we don't have time. I just want to get you the basics today. All right, key concept. We are not going to give you yet another table. ANOVA has another table, and I thought that 3 tables was plenty, and having another one just for this one small section is just not worth it. So instead, we're going to use p-values. Remember, if the p-value is small, 5% or less, then we're going to reject H0. We have something unusual. Unusual means it's 5% or less. So it's unusual, we're going to reject it. Right, so again, small p-value, 5% or less, reject H0. That's the basic thing you have to remember. Obviously, if it's larger than 5% or whatever alpha is, then you would not reject H0. Okay, so to test it, we're going to use, we're going to have our H0, we're going to use the TI-8384 to get a p-value, and then from there we're going to, if the p-value is less than or equal to alpha, we're going to reject the null hypothesis. If the p-value is bigger than alpha, then we're going to fail to reject the null hypothesis. That's what I just said a second ago. Only in different words. And then please note, we can't say which one's different, just that at least one of them is different. All right, so here's a quick example. Here's some IQ scores. Alpha is 0.05, so that's what we're saying 5% or less would be unusual. And you'll see we have low blood levels and lots of data, medium blood levels and other data, and then high blood levels and other data. The lists do not have to be the same length. They're all different lengths here. Do you see that? They're all not the same length. But we have 3 lists, one for low, one for medium, one for high. We're going to compare these lists. So our hypothesis is that mu1 equals mu2 equals mu3 because I have 3 lists, right? Low, medium, and high. And then H1 is at least one mean differs. Significance level, step 2. Step 2 is now really easy. Write down alpha. Step 2, alpha equals 0.05. Done. That's it. Step 3, it'll be we're going to use the TI-84. So here, step 3, we would use the TI-84, put everything into lists, and then run ANOVA, and we'd end up getting a p-value of 0.0195. Is that unusual? 0.0195, is that unusual, guys? What's our guideline for unusual?
Yes.
Yeah, 5% or less. This is definitely less than 5%. So we should be rejecting H0. Right, so we rounded off 0.02. So then because the p-value is less than 5%, whatever, alpha, whatever less than alpha, we reject the null hypothesis. Which means that you can either say there's sufficient evidence that 3 samples can population, you can either say that, or you can just say enough evidence that at least one differs. That's totally fine. Or you could say, because remember, this is chapter 11, we're saying H0 is our claim, you could say enough evidence to reject claims that means are the same. Either one of those is fine. Any one of those 3 is fine. Either this top one they gave up here under 5, or either one of these 2 in red that I gave below. I don't care. Okay? So again, chapter 11, those can all be reject. In this case, reject the claim that the means are the same. All right. Let's do one together. Miles per gallon. How about Chris? Go ahead and read.
The researcher wishes to see if there's a difference in the fuel economy for city driving. The 3 different types of automobiles: small automobiles, sedans, and luxury automobiles. He randomly samples 4 small automobiles, 5 sedans, and 3 luxury automobiles. The miles per gallon for each is shown at alpha 0.05. Test the claim, and there is no difference among the means. The data are shown.
Perfect. Thank you. So, again, remember the hardest thing is figuring out this is ANOVA and not something else. This looks like it could be a matrix because I have data going down and I have data going across, but it's not. Why? Because, well, obviously it's not full. I'm missing some spots. But even without that, I don't have categories on the sides. You guys see that? I only have categories across the top, not along the side. Do you guys understand what I'm saying? These are not categories. I have categories across the top. Type of automobile, small, sedan, and luxury. I do not have categories going this way, which means that this is my data. These are means. So that's the other thing. It says means, right? among the means. So means would be numerical data, right? So this is going to be this one, whereas the categories, that's going to be categorical data, the chi-squared, so it's going to be proportions. So those are two different ways, right? So visually you can see it, there's no categories here, so it can't be a matrix. Second thing is it says means, literally says means. Okay, so now I have three lists. So I have three means I'm going to compare, mu1, mu2, and mu3. So there is my claim that mu1 equals mu2 equals mu3. H1 is at least one mean differs, or at least one differs. My alpha is 0.05, so just write that down. Step 2, alpha equals 0.05. So you should be writing this stuff down here under example. This is the first part of what we're going to turn in next class. So H1, mu1 equals mu2 equals mu3. It's your claim. H1, at least one mean differs, or at least one differs. And again, write down step 2. All you got to do is write down alpha. Alpha equals 0.05. Done. Next step, compute your p-value. Put your first group into list 1, next group into list 2, your last into list 3. And then we're going to do stat test ANOVA of L1, comma, L2, comma, L3. So let's go ahead and go through that. Turn it on. Clear. Oops. Second. Wait. Clear. Okay. Stat edit. I already have them in there. I should clear them out. All right, so list 1 is 36, 44, 34, 35. You guys should be doing yours with me. So you can practice it, right? You learn by doing. 43, 35, 30, 29, 40. Again, this is going to be 35% of your exam and really easy. You just got to practice it and make sure you know it. It's not hard at all. This is like the super easiest part of this whole class. So then double check your data. 36, 44, 34, 35, 43, 35, 30, 29, 40. Yep, 29, 25, 24. Okay, good. Now I have my three lists. They're not the same length. That's okay. Stat, test, and then go up one. Go up because at the very bottom is ANOVA. There it is right there. Hit enter. And then list them all out. Second L1, comma, second L2, comma, second L3. Get all your lists in there, L1, comma, L2, comma, L3. If I had 4, I'd do comma L4, but I only have 3, so I'm done. Hit enter, and boom, there I am. S value, you can write that down if you want, I don't care. P value, that's what we really need, 0.0375. And then my degrees of freedom is 2 if I want that. Okay, so again, I'll show you guys one more time. Stat, edit, put your lists, put each one into its list, and then stat, test, up to ANOVA because it's the very bottom, and then second L1, comma, second L2, commas above the 7, comma, second L3. Enter, and there you go, you got it. Boom, right there.
What from this do you actually want us to have written down, like first step?
I want you to write stat test ANOVA L1, comma, L2, comma, L3, and then write down what you get. Write down p-value equals blank. And maybe ideally you can write down L1 above here, L2 above there, and L3 above there, just so I know what you put into there. But, you know, that would be the helpful thing. Again, this is how you get your lists, ANOVA, and then this is your p-value that you want. Okay, and then we're going to make the decision. Oops, this is totally not in the right spot here. That's super annoying. Can I make that smaller? Make it smaller? Over.
So we don't have to write the F factor values, only the P
Right. You only need the p-value. You can write the f value if you want it, but you don't have to. So then you make your decision. Thank you. So you're going to reject the null hypothesis. There's no picture for this either, right? So this is the last one, and it's the only one that has no picture. No picture on this one because we don't have a critical value. All we have is alpha. But so then you do have to say this. You have to give a reason. Since the p-value is less than alpha, and give me the numbers, 0.0375 is less than 0.05, reject the null hypothesis. And then summarize your results. You can just say enough evidence to reject the claim that means they're the same. That's totally fine.
Can you go back to the first steps of this, like the first two?
I can in a minute. I want people to be able to copy this down first. I'll give you guys another 15 seconds to copy this down, or 10 seconds. Five, 4, 3, 2, 1. So before this. Is that you wanted this one here?
Yes, thank you. Can you scroll down a little bit?
Oh, whoops, I went too far. No! Shoot. Stop. Not here. The next one. The next one?
Yeah,
That's it. No picture. So you guys, don't forget that you need to do Lab 10, and the video is in Canvas. So watch the video. It's 2 videos from last class, last semester. The first one's like 5 minutes long because I didn't have much time. And the second one, back to back with that, is the other one, which is like 7 or 8 minutes long. Watch them both because I think they're both kind of useful in different ways. And that, I think, will help make more sense. And try to get it done by Tuesday. That way, if you have questions about it, you can ask me on Tuesday. Right? Because if you don't try it until the late, to the late due date, then you don't have time to ask me questions about it. So again, here's a summary of the steps real quick, right? Step 1, U1 equals mu2 equals mu3, H1 at least when mean is different. Find alpha, compute the p-value, put L1, L2, and L3, input those, and do stat test ANOVA on those, and then make the decision. Reject the null hypothesis in this case since the p-value is less than alpha. So there is enough evidence to support the claim that there's a difference among the means, or you could have done what I did and make the top one the claim, H not the claim, in which case you'd say reject the claim that they are the same. Either one's okay. I'm not going to be picky about this one. All right, have a great weekend. And the exams. The exams, I am so close to finishing grading exam 3. I got tripped up because I caught some students cheating, so I had to spend like 4 hours yesterday looking through video. I went into campus to find video, to stare at video and everything and try to figure this out. So I did not spend that time grading, but I will get, I have the 2 o'clocks and the 5 o'clocks done. I just need to get the 7:30s done, and we had some people from all the classes taking the 7:30 exam. So I'll try to get those done maybe by 4 o'clock this morning, tonight. I will try. If I get tired though, I'm just going to go to sleep because I don't do well when I'm tired. So I'll try to get it done tonight if at all possible. If not, then it will be, tonight. If not, then it will be tomorrow for sure. Okay. All right. Thank you guys.